Okay. Clicking a couple buttons here. So we're going to start up, I believe, on page 27. Got the pause button there. Okay. Sim's ready. Okay. So last time we talked about one-dimensional motion. Just looking for my markers. So there. We talked about one-dimensional motion. And we talked about this equation in particular. Maybe I wrote it in a different order. But this equation only applied in one special set of circumstances. Does anybody remember when this equation applied? Constant acceleration. Okay. Related to, in this particular case, x sort of indicated horizontal motion. But there's no reason we couldn't have written that same equation this way. And again, it doesn't matter what the order of the terms is. You could switch to v initial. You could write this as y final minus y initial, or this is x final minus x initial. So this would be, well, the same conditions would apply, constant acceleration. Typically, we think of y as being up and down. There's one special case that we use very oftentimes because it relates to life near the Earth's surface, and that's called freefall. Does anybody happen to know what freefall means, or do you have an opinion on what freefall means to you? Anybody? It could be Zoom or here. What's that? That actually, the first part might be okay, but not the second part. So he said falling and you reach terminal speed. It turns out we don't want to think about reaching terminal speed. Free fall, we actually assume no air resistance, and then you'd never hit terminal velocity. So maybe I'll say it this way. We say gravity is the only force acting on the object. A special exception that we use for most physics classes is if air resistance, which gets right to what you were saying, negligible. I'll get out of the way in just a second. If air resistance is negligible in a situation, in those instances, free fall is approximately valid. It wouldn't be exactly valid. So, and here's why I'm bringing this up. A great many physics chapter 2 problems talk about objects being thrown upwards or dropped off a building. And we make this huge assumption about the acceleration. If gravity is the only force, right? And we're using a normal XY coordinate system where X is to the right and Y is upwards. Does anybody remember what the acceleration is in the Y direction in free fall, maybe from a high school physics class? Something about 9.8, right? Now here's the deal. We got to make sure we get this right. 9.8 isn't quite right for a couple of reasons. What's one of the reasons? The units. Excellent. And the other one is, what direction do we typically think of gravity pulling on a person? Downwards. Now, we typically say the magnitude is G and the direction is down. All right, and maybe what I'll do is I'll write it like this. The minus sign comes from the fact that, or where does the minus sign come from in here? Remind me, what was the way I wanted you to think of it? Not just that it's downwards, but that, yeah, it's pointing opposite the axis. Good, both of you. So remember that sometimes some physics problems flip the coordinates upside down and we call down positive. Okay, you might be saying why. I'll explain that later if you have time. All right, now here's the thing. Do you see anything in this explanation that talks about the type of object when we're talking about free fall? For example, do you see it referencing baseballs versus bowling balls versus tacos versus markers? I don't see anything up there. The claim is that all these objects will accelerate at the same rate. Do you believe that? Do you believe that a bowling ball and a feather would accelerate if you drop them at the same rate, or a marker and a piece of paper? If, what's that? If you could get rid of air resistance. Huh. How can we get rid of air resistance? Vacuum. Oh, gee, I wonder what's sitting right over here. Let's see if I can get there. All right. Is that the right board? Gosh, it's so weird. Oh, I'm totally on the wrong board. Man, something about this Zoom just messes with my head. All right. Here we go. Now, before I get too far along here, I'm going to be careful here. I don't know if you can see this, but see there's a washer in there and this weird little piece of orange fluff. It's kind of like a synthetic feather. Now, right now, there's a magnet up top. I don't know if you can see that magnet right here. Right? And the idea is if I take this magnet off here, the magnet is connected to a screw and the washer is connected to a screw inside there. So right now, the washer is holding up the string that's connected to the feather. So basically, as soon as I pull this magnet, they're both going to fall down. Right? It's super delicate. I got to try not to. Right? See it at all? Kind of. All right. Got it? So I don't know if you guys are going to be able to see this from the back. I'll show it to Alan too, because I think he was stuck with me on Zoom. I don't think we got to see this one, right? All right. So what I'm going to do now is I'm going to put this in a vacuum here. It's not going to be perfect. I bet I can get at least half the air out, maybe 2/3. So I'm going to let this run for about a minute. And so right now, I'm just pumping out the air inside. If we let this run for a minute, the longer I let it run, the better job it does. Hopefully we can get most of the air out. I've got the valve open good. And then what I'm going to do is I'm going to pull the magnet, and hopefully, if I'm not lying to you, if we can make air resistance negligible, which thing should hit the bottom first if air resistance is truly negligible? Which one will hit the ground first, the washer or the orange thing? I can't hear it all over the phone.
Orange battery.
Yeah, both of them at the same time. Yeah, it's tight. Good, good. Sweet. Sorry, this pump is particularly loud right next to my ear. All right. So just going to give it another 10 seconds. You know what I'm going to do? I'm just going to keep the pump running while I do this to ensure I get maximum vacuum. I could close this and release it, but not only will that take more time, but let's do this. Zoom, can you see this at all? I have no clue. We're doing the best we can. Okay, here we go. Ready? little bit of residual magnetism that made the washer not fall off at all. That cracks me up. Oh, it worked great from the earlier class. So, okay, what I tell you what, I'll try it again on the break and we can see if that works. But otherwise, that's cool. I happen to have a backup in case this fails. So let's go to that. And so, Alan, I might ask you if I'm actually visible here on the Zoom right now. Can you see me on the Zoom, or is it too, how about, can you see both the spheres? Yeah. All right, can you see the table
Yep.
at my feet? All right, good. All right, here, check. You agree that's a basketball? Yeah. Pretty uninflated. You ready? This one's heavy. It's a medicine ball. Got it? Yeah. Oh. Do you agree this is a lot heavier? Okay. So now, got a medicine ball and a basketball. I'm going to try and drop them at the same time. Do you think air resistance is negligible for this height of a drop? What do you think? Yeah, probably. If air resistance is negligible, which one of these should hit the ground first? Same time. If air resistance was not negligible, which one would hit the ground first? Medicine ball. This one's super dense, right? All right, here we go. So listen, actually, if you listen, you'll probably be able to detect it better than watching it. Try to watch, but also listen. If you hear one bounce, that means they're hitting basically at the same time. Zoom, it's still good on Zoom, Alan? Okay, here we go. 1, 2, 3. Pretty close at the same time, right? So that's an easier way to do the coin and the feather without having to go on the feather. Oh, thanks. Okay, just kick it up. All right, you didn't realize you were getting your workout in today, did you? Throwing the medicine ball around.
What's a medicine?
Medicine ball? You ready to catch? Here you go. Ready? Got it? It's just really big. Oh, sorry. No, that's all right.
What do you guys use it for?
This demo. Yeah. You wouldn't realize this, but before COVID, I spent years and years and years building up the demo collection in this building to be as good as any university anywhere. It's never going to be as good as like Harvard and MIT because they have extra staff and stuff, but it's pretty good here. So hopefully you guys will get to see some fun demos, and Alan, hopefully you'll get to see a lot that you didn't get to see. When we start breaking stuff and smashing things, it'll be fun. All right, now to be clear, I don't have time to do everything on the board for you. So this is one of these topics where I want to warn you about some stuff. In particular, I'm going to expect you, this, basically, we did a bunch of these problems last time. The main difference here is this and this. So I'm going to point out a problem in your book that I want you to do at home to make sure you actually get it. Look at page 27, 2.13. Okay. We're not going to do this. And let me get the right whiteboard. .13. You'll notice that in 2.13, I didn't draw the picture for you. So what I want you to do is be honest with yourself at home tonight or tomorrow or something, and actually do this problem. Actually draw the picture yourself, then check if you made the same kind of picture I did. Then do step B and check it every step along the way. And there's one main difference in these problems. And these problems, again, I mean, are the free fall problems, which are on pages 27, 28, 29. So basically, if you need extra practice problems, that's, yeah, well, anyways, pages 27 through 29 are free fall problems in this workbook. All right, I'm just going to make up a fake problem so that you can make sure we get this one thing. Imagine I take a ball and throw it straight up and it reaches some max height. Maybe there's a height of the building, which we would call H or something, right? Maybe there's some initial velocity on the ball, like 10.0 meters per second or something. Maybe this height is 3.4 meters or something, I don't know. Here's what I want to work on, just really quick. Delta y, v initial y, v final y, a sub y, and t. We know from our experience in our last class period, or hopefully you're starting to realize, if you can understand this table of information, if you get the list of knowns and unknowns correct, your odds of successfully completing the problem go way up, right? So typically, the coordinate system that we might use might look something like this, where this is the x direction and this is the y direction. I want to focus in particular here on this term right here. When we're filling in these knowns and unknowns, what should I punch in for a sub y? Is this a free fall problem? Let me ask you. Do you think we're going to ignore air resistance? Hint, the answer is yes for any test questions, because otherwise they're too hard and you have to code it. So we're going to assume air resistance is negligible. If that's the case, after I throw this ball up in the air, is there any force other than gravity? No. So throwing a ball upwards, that's a free fall problem, right? Air, think about this marker. Air resistance is pretty negligible on that thing, right? Okay. So this is free fall. What do I write down for a sub y? I heard negative 9.8 meters per second squared. That's great. What if you had to write it down algebraically? What would you write down if you were doing this algebraically? It's downwards with what magnitude? G. So would I write down G or negative G? Negative G. G is just the positive number of the units. All right, that's basically, as long as you've got that solid, the rest of these problems work out exactly the same as last lecture. So far, so good? All right, all right. Now, maybe you're wondering, I don't know, dude, how much is air resistance? How much does it really matter? Maybe I'll make a comment about that. First, I want to do a quick unit conversion. If we have 10.0 meters per second, and I want to convert that to miles per hour, kind of goofy units, let's do the conversion together really quick. Does anybody know how many meters in a mile? Anybody run track? Or look at the back of your book. Excellent.
1609.
Yeah, 1,600 meters is approximately a mile. Okay, so that's 1 mile. How many seconds in an hour? 3,600. If you don't have it memorized yet, you will in a couple of weeks. Do me a favor, punch that in real quick. Go, go, go. $3,600 div 1609. I get about 22. Round it off. All right. So keep this in mind. You don't have to be perfect here, but we don't think in meters per second usually in this country, right? So we usually think in miles per hour just because that's how a lot of us grew up. So what? Let's use this information and just notice it's about a factor of 2, right? So if you get a speed of 10 meters per second and you're trying to get a feeling for that speed in this class, just double it. That's about 20 miles per hour. I want you to think with me. Imagine you're driving at, say, 20 miles per hour in a car and you stick your window or stick your hand out the window, right? If you're driving and you have your hand out the window, do you think you would feel a lot of air resistance, none, or some at 20 miles an hour? What do you think? Your opinion? Some, all right? Now, I happen to know the resistive force is usually proportional. We'll call this air resistance. It's a real drag. All right. It's proportional to speed squared. So there's two things that I want you to get out of this. As you go faster and faster, it's going to matter more and more. The slower you are, the smaller this number is. But at some point, this is going to rapidly blow up, right? A v squared function looks like this. To me, 20 miles per hour is kind of a good over-under. If you're driving 20 miles per hour, air resistance might be negligible, but might not, but at least will be approximately valid. To try and give you a feeling for this, I got a simulation. I'm kind of all over here. Do this. So any questions about this while it's up there? That's surface area totally matters, and that's hidden inside this constant B. Yeah, nice. And it also depends on the density of the fluid. So like the density of air, if you're close to outer space and there's not as much air, that drag constant is lower. So it's pretty complicated. And generally we only handle air resistance in a code. All right. That's a great question. And then before I get ahead of myself, I'm curious. Those of you on Zoom, just give me a second. How does it look if I just do this? Are you able to see this okay, or is it crappy? What do you think?
I'm able to see it just fine.
Wait, say again?
I'm able to see it just fine, though. Zoom out a little bit because it cuts out.
Cuts out a little at the bottom.
Yeah, there we go.
right.
Wait, keep zooming out.
Yeah, how about if I do this too? Is that good? Or no?
Zoom out a little bit, please. We can't see the rest. There we go.
Okay. Can you read the number size or not?
Number size. I can see the initial speed. I can see the red target. I can see
What's
the
the
diameter.
angle of the cannon there?
The angle of the cannon, 85 degrees.
All right, that's good enough. Let's go with it. I'm going to try it this way. The reason I was asking this is now I can actually point at the screen if I get the right screen. It looks like I'm on that screen over there. Okay. So now I can point to you people on Zoom and the regular class at the same time, and we could talk hopefully more natural. All right. So now, okay, let's talk about this. This angle says 85 degrees. I'm going to launch this at 12 meters per second. Okay, this is about 24 miles per hour. So we expect air resistance might matter a little bit. So what I'm going to do is I'm going to run this code twice. Once without air resistance and once with air resistance that was using that drag model. And you can just get a feeling for how different they look. Now you might be saying, wait a minute, dude, this is not one-dimensional motion. You are absolutely right. This is actually a 2D motion problem, but do you agree it's approximately 1D? The only reason I put that little angle is so that we can see the whole path. That way the path is not exactly on top of itself. So this is only approximately 1D, but whatever. So let's just run this. I'm going to shoot this thing. Okay, there it goes. And now I'm going to shoot it with air resistance as well. And we can see there's two distinct paths here. The one without air resistance, it goes a little bit higher. So yeah, even at 24 miles per hour, a cannonball, okay, it's not exact, but I want to point out something else. Okay, look at the time of flight. With air resistance, this particular time of flight was about 2.65 seconds. Without it, it was 2.8. So that's about 0.15 seconds out of about 3. Right? That's not a huge percentage. If you wanted to get the percentage, what's 0.15 div 3? Let's just do it. Or what was it? 0.15 divided by, what was it, 2.8? About 5%. Okay, so we're expecting approximately 5% errors here. Okay, so keep that in mind when we're doing all these problems. I'm not going to tell you to include error resistance. You know your answers aren't going to be correct, but they'll be approximately in the right ballpark, so to speak. Does everybody feel good with that? All right, any other questions? Well, we got this up here. All right. Now, there was another good point earlier. If you use an object other than a cannonball, the drag coefficients are going to change, right? That's what you were asking. So if you use a feather here, it's probably going to be a very different drag coefficient. And in fact, have you seen this video before? If not, it's kind of cool. I'll put it in the YouTube video later or send you a link. Geez, I send a lot of emails. Sorry about that. But here, what they did is they took this giant facility. You want to see a little bit? Let's just go. I think this is the ending of it. So they just used some kind of clamp and they released this thing from rest in this giant vacuum chamber. Looks like we got some stupid ad here. But it's pretty crazy. Like, imagine how much money they wasted to get this one video. Super insane, right? It's outrageous. There they go. Oh my gosh, that's great. Okay, how do I get out of here? Oh my gosh, come on now. Gosh, I got so many screens going. All right, there we go. So that's kind of interesting. Again, I'll put that as a link somewhere so you guys can look at it later at your heart's content. But the longer one that I showed you, I think it was this one, they actually explain it. So it's kind of interesting if you want to see that later. And they talk about the crazy vacuum chamber. All right, enough on that. Any questions on that? Sort of cool. All right. Oh, all right. So now I want to talk about graphing. So before I do that, remember pages 27 through 29, there's all kinds of problems. Take a look at problem 29, or wait, problem 2.17 at the top of page 29. That's one of my favorites there. Based on a true story. I have a friend who's now working in quantum computing that we used to call Captain Extremo. And for some reason, he decided to propose to his wife in this manner. So they parachute and he's going to pop the ring, and then there's the seal carcass. And he's like, well, will you marry me? It's so funny. Anyways, yeah, that's kind of fun. Anyways, there's some weird stories in here. Oh my gosh. See those people on the Queen Mary on problem 2.16? Lacey and Jimbo were former students as well. A lot of these problems are from my former students that I was like making fun of them in there. So in a good natured way. All right. If you're bored, maybe that'll entertain you slightly. Okay. Let's go back to, now I want to go to this. Can you still see that okay on Zoom, or is this one crappy? Let's try the other board here. Let's see if this one's better. Does that look better, Mark, or is that still bad?
Yeah, that's better.
Okay, and I noticed there's this washout up here. I don't think anything that matters is going to be there, so hopefully we could do this. All right. You know what? I'm just going to do a share screen for this one because there's. No, I'm going to try it this way. Sorry. All right. What I do need to do is. Oh man, this is complicated. All right, I got to share screen for this one. Sorry. So those of you in class, sorry, I'm taking my time here. It's just kind of confusing. All right, so you guys can still see, and you can see when I annotate. So this will work. All right. I want to understand graphing. Okay, so we're going to talk about some graphs here, and in particular, now you may want to have page 31 sitting in front of you. Page 31 is going to be the summary. So when we finish talking about this example, hopefully you can look through page 31 and it'll be the summary. If it's too intense for you right now, that's okay. Okay, so just kind of remember, our goal now is to do a big example on the board and understand it. Okay, so first, notice the following pieces of information: the position, the velocity, and the acceleration. In this case, which way is this guy going to move when I hit play? I hear to the left and to the right. So
Left and right.
what's that? Oh, what's that?
You move to the left and then right.
Okay, so you think it's going to move left and then reverse direction? Sure. What's the number that tells us which way he's initially moving? Again, which number, position, velocity, or acceleration, should we associate with moving? Which word? Velocity. You might be thinking acceleration. Acceleration has to do with change in motion. So I'd rather, when I say the word moving, I want you to think moving, velocity, negative, left. So far, so good? Now, is this person going to be speeding up or slowing down? I heard slowing down, then speeding up. Yeah. So this is what I want you to think. If velocity and acceleration are the same sign, speeding up. If they're opposite sign, slowing down. I don't want you to think of positive acceleration as speeding up. In particular, look at this problem. Let's run it and watch. Slowing down, slowing down, slowing down. Now that they're both positive, speeding up. Oh, runs into the wall. Okay, so one of the things that we want to do is understand this motion with graphs. Okay. Now, I believe I have the same numbers set up as before. 4, -6, +2. So let's just run it, and then we're going to play it back over and over and over again in slow-mo and talk about the different features that we see in the 3 graphs and how the 3 graphs relate. Okay, here we go. Moving left, slowing down. Oh, did you see that? Stopped for a split second. Turned around, speeding up, comes to rest. All right. Now what I want to do is I want to change the axis so it's easier for me to read. That looks pretty good. And then here, I think I need to zoom in on this one. I don't know if
acceleration at the end, did that bounce?
That's a good question. Let's replay it. Now, I'm going to hit playback, and I want you to notice something immediately. Number one, you see how these numbers are rounded a little bit? I don't know if you can read these numbers out there, but that says 3.7, and this says -5.9. Okay, so really, we started with -6 and 4. Because we're doing playback, and you can see it's got to do a little bit of a time step here. There's a weird little numerical error. Just trust me, these are approximately 4, -6, and 2. This one doesn't have the error because it's not changing. Now the question was, what's that weird little thing at the end? Well, let's watch. Now I'm going to slow down the playback speed. What is the weird thing at the end? What happens to the dude? What happened to him? Yeah, he runs into the wall. Usually, when you run into a brick wall, you stop. And you stop very quickly, right? So for now, what I want to do is not talk about that and come back to it at the end. So let's kind of ignore this crap right here. That has to do with the wall. Agreed? So for now, pretend this guy doesn't hit the wall and let's just talk. All right. So now, the first thing I want to point out, whoops, is this number right here. That is -6. Notice that is, oh, whoops, let me get this back to the reset. Okay. Notice, initially, the velocity is at -6. That is the vertical intercept here, right? So that is V initial Y, or X in this case, sorry, V initial X. Notice this other weird thing. The person is moving left, right, but the graphs are all going up and down. So notice the time axis is the horizontal axis. In this case, we don't say X is on the X-axis anymore. Time is on the horizontal axis. And here, the vertical axis, again, the initial position, that's X initial, right? The initial position. Now, in this case, if we ignore the wall, do you agree the acceleration is constant if we ignore the wall? So we're going to assume this looks like a constant acceleration problem, at least up until we hit this region, right? This wall region, circled in black. Okay. All right. So far, so good with that. Now, what was one of the equations we know from last lecture? What was one of the fundamental equations I said that relates velocity to acceleration or position to velocity? Do you remember one of those two fundamental equations that had a derivative? How about this? Do you remember acceleration is supposed to equal the derivative of what? Yeah, say again, louder. Velocity, yeah. Okay. All right. Well, remind me. What does the derivative mean on a graph?
Slope of a tangent line.
Slope. Now I want you to think. There's three graphs here. Saying slope is not enough. Slope of which graph? Slope of the velocity. If I'm taking the derivative of velocity, I need the slope of velocity. So that means I should use which plot? AT, acceleration versus time, XT, or VT? What's your gut say? Go with it. It's okay to be wrong. VT.
VT.
So now let's check. What's the rise on this plot? If I go from t equals 0 to this point, what's the rise that I'm trying to draw right there?
2x.
Wait, I heard, wait, say again. Somebody said a number. 6 is not right. It's close.
It's 2x or 2t.
No. What? 6 meters per second. Remember, in physics, the units matter. Now, I know in calculus class, you never did them, but it turns out if we remember to always think of the units when we're doing our slopes and our areas, it will give us insight into what the heck that thing means. Just trust me on this. All right. What's the run? Right there. 3 seconds.
Meters. Oh, 3 seconds. I meant to say.
Yeah, because remember, remember, if you look down here at the bottom, see the time axis? So this is 10 seconds, 9 seconds, etc., 8 seconds, if that helps. They only labeled it on the very bottom one because they're running out of room. So this is a 3-second. Now I would normally write below there, but you know, some people are red, green, colorblind, about 10% of people, so I got to put it there. Okay, what's the slope? And maybe that's where maybe you were like rushing ahead to the slope, right? Slope is rise over run. Sorry, it's so slow. All right, what's the slope going to be?
2 meters per second squared.
Yeah, so we get the 6 meters per second. And notice the units work out. Oh, geez, that's sloppy. 2 meters per second squared. Notice the units actually work out. Sorry, that's sloppy there. All right, is everybody okay with that? So that's one of the things that I wanted to emphasize today is when we do problems with graphs, I want you to keep the units on the numbers because that could give us insight. So far, so good? Okay. Well, can anybody remind me what the similar equation was for velocity and position? Right? What was the equivalent of that equation down there? What was velocity equal to? Derivative of x or position. Yeah, nice. Okay, and then what is derivative of x with respect to time? That's going to be the slope of which graph? xt, position versus time. Nice. Okay. So notice this one's a little bit trickier. So maybe let's pick a particular spot, right? If I pick this spot right here, how would I get the slope right there? Well, I could pick 2 points that are close to it. I could get this point and I could pick this point. And I could estimate the times. I could estimate the verticals, and I could estimate rise over run. And it's funny, when I did this in the last class, everybody felt like everything should always line up on grid lines. The whole point of a graph is you could estimate the numbers when you read a graph. We'll do an example like this afterwards, but in the interest of time and knowing that we're going to do an example later, I'm going to point out one key point. What's the easiest time to get the slope on the xt graph, on the position versus time graph? What's the easiest slope that you can just see? At what time? At 3 seconds. Why is 3 seconds really convenient? What's the slope right there? Slope equals 0. Right? So if the slope is equal to 0 there, what should the velocity be there? It's 0. So notice we can at least check this one really quickly that way. When you have 0 slope on the xt, we should have 0 velocity on the vt. So far, so good? Okay. All right. If you want a screenshot, take it now. I'm going to get rid of it in 3 seconds here. 1, 2, 3. There it goes. All right. So that was derivatives. What's the other thing you do in calculus usually? Other than Taylor series? Yeah, integral. All right. So now let's talk about an integral. Well, I'm going to do it like this. We know that A is equal to dv dt, and I'm going to stop color coding because it's going to drive me crazy. Okay. A is dv dt. I'm going to rearrange that and just cross multiply and say dv equals A times dt. Right? No rules broken. Math is math. Now, if I want to learn about the velocity, I could integrate both sides. When I integrate both sides, remind me, on a graph, what is the integral of A dt? What is an integral on a graph? Is it a slope? Area, nice, nice. It's the area. Now think, which symbols appear in that integral that I'm underlining here? A and T. Which plot is that the area of? Is it the area of the XT plot, the area of the VT plot, or the area of the AT plot? AT, right? Do you agree? If I want to do an integral on A, I get the area from the A plot. All right. What is the integral of dV? Speak up. It's not V.
Oh, good job.
What does your calculus teacher always criticize you when you forget? It's not just V, it's
Oh, plus C.
V plus C. You remember that? Now, and maybe you said it and I just didn't hear you. This fan's really loud. All right. To avoid having to think about the plus C, there's a trick that I'm going to do in most of my physics integrals. All right. If we put limits on an integral, say from an initial value to a final value, I don't have to worry about the plus C, right? Remember that in calculus? If you have a definite integral with known limits, well, think about it. In our experiment here, there's tons of different times we could use. There's tons of different velocities. We should be able to get numbers to plug in. All right. So in this case, that would be V evaluated at the initial value and the final value. Agreed? Well, isn't that V final? Whoa, where's my marker? Come on. Isn't that V final minus V initial? What the hell is that? It's not V, but it's another way to write final minus initial for anything. Change in, or delta V. So I want you to think, at least in this chapter, of the integral of dV is not V, it's delta V, because we're going to put in limits. Does that make sense? And watch what happens here. It matters. So let's say I want to get this area right here, right, that I'm shading in green here. I want that area. Okay, we're on the AT graph. So I'm going to use capital A for area, lowercase a for acceleration. Capitalization matters in class as well as in code. Okay, how do you get the area of a rectangle? Length times width. What's the length? It's not 3, but 3 seconds. What's the height? It was 2. Yeah. What do you get? 6 what? Meters per second. Does everybody agree with that? All right. Now, what is that? Is that the velocity after 3 seconds? It's not the velocity. What is the initial velocity? V initial is equal to -6 meters per second, right? What's the final velocity? 0. What's the change? +6. Do you see how that delta V is crucial now? So remember that, right, we've got to have the change in velocity. So notice this 6 meters per second does not equal 0, but it does equal delta V. Good on that? Everybody cool with that? All right, so we're going to do that again for X. If you need a screenshot out there on Zoom, go ahead and snag it. Give it 3 seconds there. 1, 2, 3. Any questions while I've got this up from anybody on Zoom or in person? All right, all right. How painful is it seeing this little writing on Zoom? Can you actually read it out there, or is it visible to you guys? Anybody?
I can read it.
All right, I'm trying to do the best I can with the, yeah, right. Now you can see why I was asking about using the ruler, but it's just flipping screens back and forth with the whiteboard in this is too difficult for me. So that's why I'm not always going to do this, just this time pretty much. All right, let's get our other equation here. Do you remember that V was equal to dx dt? I'm being a little bit lazy. There's an implied I hat on these. Do you agree? All right, these are vectors. So let's do the same thing. So what is dx? Dx should equal what? Based off doing math. It's v dt. And then we can integrate. We're going to put on limits, initial, final, initial, final. What is the integral of dx if you had to guess right away? It's not x, but delta x. What does delta x mean? Is it distance? Change in what? What is x? Position. So what is change in position? Is that distance?
Displacement.
Displacement, right? And the main difference here is that displacement could be positive, negative. Distance is always positive, right? And what do you think this is? The integral of v dt is the area under which plot? Which one?
Velocity.
VT. All right, let's do it. Get me this area all the way out to 3 seconds. How do we do it? What's the area? What's an equation I could use to get the area of that shape? 1/2 base times height. I got the 1/2. What's the base? If we're going all the way out to this point right there, what's the base? 3 seconds. I like that you're getting in the habit of including the units. It's just a little annoying, but once you get used to it, it's fine. What's the height?
6 meters per second.
It's not 6 meters per second. -6. Remember, with math functions, you could have a negative height, right? Because it's starting at negative, right? That's okay. What do you get when you plug all that in? What units, what number? -9 meters, right? Well, let's go up to the top now. Where did we start? Do you remember? 4 meters equals x initial, right? At 0, what's x final? Is the change in x correct? What is delta x? -9 meters. So these are consistent. All I'm trying to do is show you that the calculus you learned and the motion that we see and the charts are all in agreement. Okay, nothing fancy here. So far, so good? Do you know? Oh, okay, so if you need a screenshot, grab it. I'll give you 3 seconds there. 1, 2, 3. All right. Any questions while I got that up from anybody? I haven't forgotten about the wall. We'll come back to that. One last thing. Up till now, we've been talking about how X and V relate, or we've talked about how V and A relate. There's one more piece of information that's sometimes useful. How does A relate to X? How does this plot relate to this plot? In particular, do you know anything about how the acceleration can give us a clue as to what type of shape the xt plot? How do you get from position to acceleration? How many derivatives do you have to take?
2.
Do you remember anything about second derivative test? What does that mean?
Determines which way is concave.
concavity. Now think about it. If your second derivative, right, is positive, are you concave up or concave down? Well, let's look. A is greater than 0. Do you agree? This stuff is concave up. So that's kind of useful. If you know the acceleration is positive or negative, that should tell you the concavity. So far, so good? All right. All right. Take a look at page 31 now in your workbook. Take a look at that stuff. In particular, look at the XT graph, the VT graph, and the AT graph bullets. Okay. Forget about that little table at the bottom right now. I'm just giving you a second to look at it, see if that makes sense. That's supposed to be your summary of everything we just discussed. I'll look too and see if there's anything I forgot. XT graph, we talked about time is on horizontal, X is position, not distance. Talked about vertical intercept and slope. We talked about concave up. Oh, I guess I should mention this. If you have constant velocity, your acceleration is 0, you get a linear XT graph. Parabolic is constant acceleration. Area XT isn't useful, right? Just because we can get that quantity, you could get the area under the XT, but I don't know what to use it for. Maybe somebody else knows something that I don't, but I never use it. Okay. The VT graph, V is velocity, not speed, even though we don't really draw the arrows all the time. Vertical intercept, we talked about that. The value of V tells you the slope on the XT. We talked about area is displacement, which is change in position, right? Again, we got to be careful there. The area is not the position, it's the change in position. And then the AT graph. All right, feeling pretty good on that. Hey, how are you all feeling? Thumbs up, thumbs down. Hopefully this is some review, maybe a little bit new stuff. Watch those units, okay? The units will set you free. All right, what else did I want to say? Let's talk about the wall. Somebody asked about the wall, right? Does this make sense? Let's think about it. And in order to see the wall, I need to zoom out a little bit. Okay, it's a really big negative number. All right, so let's look at this. We're focused right now just on this part right here. In particular, do you notice that A is negative and huge? Okay, we have a huge negative acceleration. Agreed? How should that relate to the slope of the VT plot? If you have a negative acceleration, what should be true about the slope on the VT plot when you hit the wall? Down. Should it be a steep slope or a gentle slope? Steep. So notice this right there is steep negative slope. This makes sense, right? Okay. When you hit the wall, as you run into a wall, are you moving forwards, backwards, or are you at rest? This is tricky. When you hit the wall, technically, part of your body is being smashed. And so your center of mass is still slightly moving towards the wall, right? Not very much, though. In particular, let's analyze it this way. What do you notice about the area under this curve? Is it big or small? Yeah.
Want to be small.
It's a tiny area. So what does that tell you about delta X? Delta X should be tiny. When you smash into the wall, you are not moving that much, right? You're coming to rest very quickly. And that's why when we look up here, you don't really notice any changes in the position, right? Literally, your body might move a few millimeters or something as your center of mass smushes into the wall. If you want to test this, you run into a brick wall. I don't want to do it, okay? I don't recommend that. All right, but whoever asked about the wall, is that kind of elucidating that part? Is that good enough? Doing good on that? All right.
I'm just
Yeah.
wondering why the acceleration dropped to negative.
Okay, let's think about it like this. How about this? Oops, I thought I cleared that. Okay, let me go back to here. Let's play it back fast and then slow it down right at the end. Okay, we're coming towards the wall, right? What direction is your motion? Is it positive I hat or negative I hat? Okay, so what is your velocity? A positive number or a negative number? Okay. Do you agree you're about to slow down? When you slow down, what's true about acceleration and velocity? Do they have the same sign or opposite sign when you slow down? So now when you hit the wall, you need to go from a positive number to 0 very rapidly. In this case, you need a negative acceleration, right? So as we go here, right as you hit the wall, all of a sudden you have a massive negative acceleration so that you go from moving forwards to at rest. Does that help?
Yes.
Cool. Well, let's flip this back. All right, let's run it back and let's clear everything here. All right, so now what I'm going to do is I'm going to start with -4, +6, and -2. Think to yourself, how is the graph going to change? Talk to your neighbor.
Sorry.
Just talk to your neighbor, not me. Okay.
Go
What do you think's going to happen?
positive.
And so, Alan, the second half today, we'll be doing a lot more circling. So, yeah. You guys got it? You talking about it? Think about XT, VT, and AT. Include the wall if you get done, right? Think about what should happen when you hit the wall. Okay, should we give it a shot? You ready? If I didn't give you enough time, my bad. The acceleration is negative. The XT plot is concave down. The velocity plot is sloped downward as he gets towards the wall. What should happen to the acceleration when he hits the wall? Think to yourself. Large and positive, right? Notice again, when he hits the wall, it's slowing down, right? Here is the wall. Notice that velocity is negative. Notice that acceleration is positive. So in this case, a positive acceleration caused the person to, or represents the person slowing down. So it's not the sign of acceleration that tells you whether you're speeding up or slowing down. It's, did this ultimately address your question? That's what I was trying to get to. Good?
Yes.
All right. I think this is a logical spot to take a break. We'll come back in 10 minutes and then we'll just start doing some problems and I'll start circling the room with Alan and we'll do it. So let's take a 10-minute break. I got 5:35. Anybody on Zoom have questions?
None at the moment.
All right, let's take that break, come back, and then we'll just start hitting it and see if you actually can do anything. Okay. Oops. All right, so let me say a couple of things as we get started here. So the rest of this lecture, for the most part, it'll be pretty boring. There might be a few instances where I say something here or there and I call us together as a group. But at this point, right, you probably think you know what you're doing. You might know what you're doing, but we've got to find that out, right? And if you don't know what you're doing, it takes some practice, right? Rather than me yakking up here, going at my pace, I want you to go at your pace. So 2.25, I would call a starter level problem. It's not necessarily super easy compared to the exam level problem. I think it's just a little bit easier. And if you're not sure exactly what you're doing, I tried to go to an extra painful level of detail in the solutions. So now, don't get me wrong, all these solutions were painful to write. But so I put in a hell of a lot of detail on this. So if you're not sure where you're at, maybe start here. If you're confident and you think, I'm really good at this, maybe jump right to these two and see. Now, remember, after you finish, and if you're somewhere in between and you're not sure, you can do this one. If you're not sure, use the solutions on 225. So if you think, I just don't know this as well as I would like, get the solutions out, go through 2.25, read the solutions, do it. And if the solutions don't make sense, ask me something. Ask Alan something. Alan's good at this. All right. And then work on to this one. So use the damn solutions. All right. And then eventually what you want to do is hopefully you can at least try these two without the solutions. So if you're really confident, go ahead and try these without the solutions and see how you do. And we've got laptops over there, or you can use the desktops, whatever. Right. And talk to us. So on Zoom, what we're going to do is we're just going to start circling the room. And we're going to check in on Zoom. Alan's going to hit Zoom every time he gets to his desk. I'll check Zoom every time I get to my desk. And we're just going to go around and around and around. If for some reason you want to just check out now and just work on your own for the next hour, just do it. Just don't kid yourself, right? You got to work at least another hour here or else you're going to be clueless. So this is the time to do some work so that you can ask me questions. So I encourage you to not flake out. And if you want to work on your own, that's fine. You can always come back into Zoom and we'll add you in if you have a question. All right. So the rest of this lecture on YouTube is going to be pretty boring if you're watching it later some other semester. All right, let's get to work. Okay. Talk as much as you want. Get whatever groups you want. Get a solution out. All right, Alan, let's loop around and see. Which one you want to try? 225, right? Okay, sound good. All right. And if you haven't already done your lab groups, if you want to talk to somebody and sign up on lab, I sent some links earlier today. You can do that right now too.
Do you think I should?
I would do at least, yeah, so there's a good question. If you look, right, the solutions or the required homework problems do not include these. I think you should, if you're going to skip these, you should at least do these two and make sure you got it. So we want to at least do a couple of these in class today. That way you got those other, yeah. Just because I know what's in these solutions and there's some weird little stuff that will help you get some points on test day. Good? Okay. Yeah, right. It just helps you learn how I expect you to answer things on test day. So yeah, all right. Good question. And then if you get those two done, then jump ahead, right?
Yep.
Yeah. Yeah, because I was looking at the same thing. I forget what those problems are. There was two of them that looked really good. I forget what they were. What was that one? Did I say 33 and 34? Oh, yeah, I should have said 33 and 34. Yeah. Whatever. Yeah, I should probably add a couple problems into that list of bare minimum. Basically, you got to do 28 and 29 or 33 and 34. Those are the ones that have the XT and VT graph. So pretty much every test I've ever given, I have either an XT graph or a VT graph, and you have to do something with it. Cool. So this will just make sure you got that skill locked in. Good question. It's your laptop, so you have it. Yeah, might as well have it made so it's easy to read. Just check it every part. That way, if something I say doesn't make sense in the solution, just ask me about it. I'll get it set up. You can hit you can hit Control F. So you type in, I probably should have spent more time. Yeah, that's why it's.
Yeah.
All right. Okay. You? Sounds good. Sounds good. You know, another thing that people often do too is they ignore the units very simple. Right. They doing here, okay? Okay, let's start you looking, okay? Okay, okay, got you. All right, sweet. No. Yeah, exactly. That's what I meant. I have to, yeah, because it saves you a lot of wasted time, right? So if you can use the solution for this one while you're working through it, that's great. And then hopefully you can move to one of those other ones right after. So definitely do exactly what you did. Do not share it all immediately. What's up? Yeah. That'll be interesting. Yeah, it will be. So basically, understand physics. Yeah, exactly. So remember, if you don't know something right away, there's two things. One, you're probably smart enough, but the question you could ask would help them figure out how to get the right answer. Like, document where that might be listed, or let's look for a document together, or another thing you could do is basically just, I'm confident in your ability to criticize, right? So you're not yeah. Now, okay. Did you get the ones with the coding, the coding ones with the 5 different ideas I had for coding, the simulation?
I think you said I saw that.
Yeah. So, if you want to, well, you know the order. Yes. So the idea is, what's going to be tricky is the forces in each state. You know, basically, you can figure out the force. Yeah, so you just say, so, oh. I no, for all I know, the school may tell us that not you never know these things. So just be, yeah, and be confident in your abilities, and if you don't know something, just don't like it.
Yeah,
I don't know, but you know what I'm saying? You'll be fine. And then if you're really stuck, you just ask. And then hopefully I can tell you that you'll understand quickly. Should be. Yeah, the other thing is, like, you know how to use Travis?
Oh, never did try.
Okay,
So
so
figure that out.
that would be good. Why don't you figure out Tracker and don't just pay yourself to figure it out.
Right.
Yeah, yeah. All right, so, yeah. Shoot a short 3-second video.
Yeah.
And I think I have instructions somewhere. It might be in my, let's check here. Yeah. Look, okay, so you can come up here. You know my channel, we got the playlists,
Oh,
and
right,
then
okay.
it might be in lab training videos. Let's see. Using Tracker.
Okay, yeah, it's just.
Yeah, so you'll be able to find that?
Yeah.
Okay. Yeah, so you could just try making your own video, and I think if you want, you could even, if you don't want to make a video, right?
Yeah, you have them here, lab.
Yeah, so robjosted.com, 161 lab. Thought I did like a fake, whatever. I thought I had like a video already here for you.
You
Just-
did, I remember.
Oh, there it is. Here it is.
Yeah.
Okay, so here we go. Blah, da, 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 da. It's right in the 1D oral press. Here's a ball drop on head. So if you want to use that way you can see if you get the same data as me too,
True, yeah.
right? So you can confirm you actually know what you're doing and the coordinate system and cool.
Cool, yeah. I'll
Yeah.
definitely do that then.
Yeah, and it'll probably take you about 30 minutes. Pay yourself 45.
Right.
You know what I mean?
Yeah.
Okay, if it takes 45, give yourself an hour.
Got you. All right. Thank you.
All right, yeah, yeah. Yep. Okay, good. Oh, I see something in the chat here. So, Jose, check the messages I've been sending out. In short, no. The answer is no, but I'll just answer you in the chat, okay? Okay, Jose, I just sent you something. I hope that makes it more clear. You know, I sent out so many freaking Canvas announcements. You know, I figure you guys could delete them if you don't need them, but you might be one of the students that actually needs to read it. So I gave you a super compressed version, but the whole details are, and my philosophy on why I do that. So Jose, hopefully that addresses that. Can you just confirm you got that message, Jose, either in chat or whatever? Yeah, I know it sucks, right? This whole thing is insane. So. Okay. So Jose, if you're still out there, you can let me know if you got that. How about on Zoom? Anybody there have a question that I could help with? I'm hoping that the solutions are so good that that you can almost deal with it, even though I'm not right there helping you every instant. Okay, I'm going to keep looping. And remember, both Alan and I are looping around. If you are on Zoom and need a question, you could just shout out and just say, hey, when you get a chance, and then we'll hear you and we'll come get you, okay? So.
Yeah, get the same thing we did. Separated into
Got it, Jose? All right, I feel like you got kind of the bulk of it there, Jose. I'm gonna do a loop around and I'll come back. All right, I'll check again. What do you think? How you doing? Okay? Wow, okay, cool. All right, sweet. Okay, should I give you a second to get your brain wrapped around it? Right. Right. So on test day, what do I like to do? I'm either going to give you an XT graph and ask about velocity and acceleration, or I'll give you a VT graph and ask you about X and A and stuff like that. And see if you can remember all those little subtleties, like is it X or is it delta X when you or is it V or is it delta X, stuff like that. Is it the slope or the integral I need to get this plane? Cool. So for example, so literally, whenever I gave a test question, nobody understood it. I added it to the book. Right? And then I'm like, all right, clearly something wasn't working here. Let's try it and see if we can do it together. Yeah. Anyways, so like if you wonder, yeah, by the way, I'll say this to everybody. In case you're wondering, these questions, they're basically all old test questions for the most part. Right? Whenever I gave a test question and people really were bad at it, I threw it in the book. And the next thing you know, I know that's disturbing that I have 1,000 problems that people had trouble with, but whatever. All right, good. Not all of them, but about half. Okay. All right. Should I let you work for a minute? All right, how you doing?
Okay, pretty good.
We probably have the same question.
Yeah,
Go for it.
I was thinking, what, at what point should we actually use it for, because like, depending on
What are you
what.
trying to figure out?
Oh, sorry.
No,
Yeah,
no,
I should
I
have
just got a
started
picture,
with
because
that.
everybody's on there. What are
So
you trying to figure out?
for 22 point, yeah.
So get the velocity at 4 seconds. Now I understand. the question.
Yeah.
Okay,
So we have to estimate it,
yeah,
but. Well, at first I just use these points because they're the only ones that
that's
are
what everybody
perfectly.
does.
Yeah, they're the only ones that are
It's just
perfectly
totally
all.
Yeah, just because it's easy doesn't mean it's right.
So, but now I'm wondering where should we go, or how do you determine
Here's what I would say, on
where?
a test, you gotta get your answer within 10% of mine on this kind of question.
Okay.
So you wanna be kind of close.
So,
There's sometimes if you're like 12% of it. Right, so you gotta, basically, you need to actually read the block. And did you see why?
Yes.
Look at, it looks like, to the eye, they don't look that different. You agree? But look at the number, the percent difference is, what did I say, 40? Isn't that crazy?
yeah,
So the idea was, I did not expect this at all. Almost every single student grabbed these two points because they're easy to read, but it turns out you're off like 40%. That's pretty bad.
so it's, as long as we get within, we
Yeah.
wanna just get within 10%.
So if I could I recommend a strategy in general? Do you care if I use your pencil for a sec? Okay. Look, you want to make two of the numbers easy. So I either choose this point and this point where they line up on the horizontal, or this point, and this point where they line up on the vertical grid. See what I'm saying?
Yeah, so that'd be about 6.
Yeah, and so you have to read either the vertical coordinates, but you can just estimate it, right? And so it's like, yeah. Is that
That's a
cool?
lot closer than that.
Exactly. And so if you basically, as long as two of the coordinates line up on grids, then it's not that much work.
Yeah.
It's when you like this would be a terrible place to pick it, see?
Yeah.
You wouldn't know it, it's far away, but, so basically, if you can get something on like an adjacent grid line nearby, either up or down, left or right, find a nearby grid line. Cool?
Yeah.
Yep. All right, and that's why we're doing this. Yeah. Good. All right, was that your question too?
Yeah.
What's up? Good. Yes, after 4 seconds, meaning between 0 and 4 seconds. Yeah, so, and this is, I agree, this is cool. I was trying to find every single possible equation I could think of. So you know, these questions right here. These are actually how it's like, let's check these. They want to also be 20. Yep. And then remember, with this first one, I would have a solution. Oh, shit. Really? Damn. All right. You ever get to a point where you need to stretch, feel free to take a very short break. We only have another 30 minutes or so. Nice, nice. Good. Yes. Sure, sure, absolutely. Yeah, the first one's such a free right away. So that makes sense. Okay. How about you? Kind of start from the- Okay. So part C. Waiting for that gets you displacement for a second. This one gives you the displacement. Sorry, it's poorly worded, I agree. Just so you know, the exam question would probably be a little bit more. I feel like it's- I was trying to make sure it's just saying all of it. Yeah, C plus D should give you the total displacement. That's not the same thing here. This picture is right. So displacement comes with the minus. This is right. Nice. Yeah. How are you doing here? Okay. Yeah. Okay. So the total displacement, you just add it together, right? Remember that this is one. Do you agree this is something in reverse direction? Because it was negative, it's positive velocity. So that's the one where you have to get the absolute value of this, but the absolute value. Right? Because remember, this is so this one, it traveled 2 meters to the left. It travels 2 meters. Here it travels 18 meters, so together it goes 20. So you see that's it. It's just absolute value. So when you're getting displacement, add together the areas with the plus minus. When you're getting distance, add together the absolute values. Good? Yeah. Good. How you doing? So the BT plot, so here, more 0, 0, something, large negative, right? So the solutions are provided. That's outstanding. So tabular on all these things, kind of used to that process. It's always first, what is the type of graph that right, keep it up. I appreciate that effort. That's awesome. That's some ideas. Yeah. B.
Yeah. The teaching and sensation. I knew that when it comes to
Okay, true, true. So when it crosses a line, there's no, no, that's not true.
no velocity.
No velocity, because, okay, here's the deal. On the VT plot, number tells you how fast you move, not the slope. So here, the number is constant velocity. Here, the number is changing with negative acceleration, negative slope. So I want you to think about this. VT plot, if I'm asking about acceleration, that's get the slope. So here, it happens to be zero, but not because it's at zero, it's because it's zero slope. You see the difference? So here, the velocity is constant, acceleration is zero right here. And right here. Does that make sense? Acceleration is the slope of VT. That's why it's here, zero, and zero. Remember that problem we did where the guy was reversing direction? Remember the velocity crossed zero? Good. Right? Right here. The velocity is zero, but the acceleration is 4. Just because the velocity crosses zero doesn't make it zero. It's zero slope. Is that good?
This is constant acceleration.
Yeah, well, this is zero acceleration, which is also constant. This is constant acceleration. This is constant. This is, and this is. This is a special constant, 0. This is different. This is also 0. This is a negative number. This is a big negative. So each one, so there's 4 stages, right? 1, 2, 3, 4. So here is one constant acceleration stage. Second one. And the idea is in general, we get this habit of taking complicated problems and putting them into stages. Is that better?
Yeah.
Nice. Nice. You ready to come back?
Yeah.
Here, the area is the, so, let me show you something. So here, I take the derivative. Going down a graph, okay? Going the other way is the integral, right? Does that help? And I kind of think of it like this. When you integrate, that's like raising the power, right? That's 1 less seconds in the basement. So this is meters per second squared. This is meters per second. This is just meters. I don't know if that helps. I like to always stack them xt, vt, at. So its derivatives going down, integrals going up. And I don't know, that's what helps me in my mind. Is that cool? If you like that and that's working for you, something you can do is kind of scribble that on your paper and remember on test day, you could like memorize that, and then as soon as they hand out your test, you could like scribble that on your test. They give you an equation sheet, you can scribble whatever you want. Is that good for now?
Oh, yeah. I think it- Yeah.
How's it going up front? Were there some sneaky parts in that one?
That is messed up. But I know I get
That's
it.
good, but you're learning from it, right?
Yeah.
So that's cool, right? You're learning the current and tricks of it, you're on the same day, and that's why we're doing it. All right.
Where did you get all the
I wanted to name my children Vega and Lycra. I was beaten. That did not work out. So I was told it sounded not cool.
So should I, so when I write an answer on a test, I should actually say words
No,
or,
you could, yeah, so as long as you remember to include units, the thing that drives me crazy is if you forget units, Yeah, so I don't care if you want to use set notation, I can get that. If you want to use words, if that's easier. If you just say 2 to 3 seconds, I'm cool with that. But it's like, if you forget the units, I guarantee I'm marking it off. So just because it's physics class, I want you to get that habit. That's all. Cool? And
Yeah.
I don't care about open versus closed intervals. I don't care about that.
Okay.
So you need to, during the step time, just have to get.
You can put the units on your final answer. If you don't, it's great. So once you've done enough practice, you realize all I need to do is do my work and then check the units at the end and put the right units on. Now, sometimes students that do that will not catch a mistake, but they didn't check units and make sure you do a step, so you might miss out on that. But usually, when you try whenever possible, not be to do it algebraically, so then you can check the units of your final answer. Plug in all the numbers on your calculator. That's what it's right. Right? So that's why we want to do it algebraic, like less right than units.
Also,
But always on the plan. So yes, you could just leave them all off the whole time. You need to remember, as long as the answer is not, and the final answer is the circle there, it's. Is that good? Good question. What else did you say?
so when you, since the vector is, or since the velocity is the vector, right?
Here's another thing. On the test day, I oftentimes say, I get it, you don't have to put I hats if you don't want to. Is that what you were gonna ask?
I was gonna say, because if you take the integral of that, would you do plus C as a vector? The vector
Yeah, you would. You would.
like that.
But now, remember that this chapter is 1D motion. So because it's 1D motion, and the graphic questions that I know I put on test one, I usually put 1D motion section. I usually say something like, you don't have to put the I-hats on this problem. Or if you just leave them off, I'll just say like, okay, I'm going to assume the positive number implies positive I-hat. So just like we normally work on the board, I will allow that same thing to hold for me. So you could just put plus C and leave off the I-hats. Is that good?
Yeah.
Outstanding. Good question. Yeah. I think I included them on some of these answers just to kind of remind you that this is a vector quantity. That's what I'm at 25, the first one. Just wanted to remind people that just because the graph is moving up and down, object can be running right. So that's why. Yeah. Is that good for now? All right, sweet. Yeah. All right, outstanding. Give it up. How you doing? Good? Good. Check over here. Looks like how. Good? Yeah. What do you think? You all right? Nice, nice. Is that what you're going to? But this, you remember that student demo where the guy was going? That's split second, technically. That's tight. The ball was addressed. Split second. Got it? So it's not. These are open. So for all intents and purposes, the ball is never really at rest, right? But if you watched it with a really slow motion video, it was looking at rest at the very top. Good. Okay. Check the zoomers. Okay. Jose just sent you a message there. I don't know exactly how many lab points. I haven't worked it out completely, but I'm expecting somewhere around 130 or 140. Actually, it might even be a little bit more. So yeah, missing one lab. Yeah. And if I give you 10 free points to recover, that's okay, right? So yeah, basically, you should be able to handle it if you miss one. And again, I'll give you those 10 freebies to cover one. It's when you start missing 2 or 3 that it's just going to start taking chunks out of your grade. So yeah, in general, yeah, I don't know. It's yeah. I hope that helps Jose the math there. Questions from Zoom while I'm sitting here. Anybody need some help or anybody have questions that I can help with? Hopefully you're getting something out of it. How about you, Mark? What do you think?
Can you hear me?
Yeah, I hear you.
Oh, there we go. So far nothing. I've been cruising at 2.25. I'm just taking my time, like rather just to let the fundamentals settle in.
Yep, and then make sure you're probably looking at the solution right away, right, Mark?
Yeah, I'm looking at them right
Definitely.
away.
So 25, 27, even 28 and 29. If you get stuck at all, immediately look at the solutions and try to get unstuck. And if it doesn't help, let me know. Okay. All right, I'm gonna keep looping around then, unless there's somebody else there. Appreciate your tenacity there on Zoom. I know it's frustrating to be working alone, and that's just, I don't know. We're all at various points in the COVID protocol these days. Hang in there, hang in there. Hopefully we can get most of the COVID absences out in the first 5 weeks is what I'm hoping. And then after the first test, maybe it'll become more normal, maybe, fingers crossed. All right, I'm gonna keep looping. Right, so it's not supposed to be fresh.
I got that wrong. 'Cause, like,
DET. If you take that DET, let me draw it.
4, 5, 7, 4, 6.
Take a derivative, you're taking DET. That's the same thing in units as a 1/seconds, right? So if you take the derivative, you get another seconds in the denominator. So if you add another seconds in the denominator, you get meters per second squared. That's acceleration. That's one way to remember it, right? You look at the units. So this is something that's like, even though the units are really painful to deal with, it's also helping you get a check. Does that help? So what's the derivative? This one. Second one, second two. Second one, what's the slope? Absolutely.
Going to them quickly, but then I realized I got like half of them wrong. Check them.
That only works for the BT. So the thing that works every time is they have the same slide. So summarize what we just talked. BT. Since they're these, so these are really- It's not gonna stick this time. But after you very detailed.
This is probably the
First thing you gotta do is.
I don't know why
Which graph like.
what's from
Which are two. Well, do you agree, if you know the displacement, that would be the delta x's, right? And then if you want total displacement, you have, if you want the distance, you would have it in absolute values. Now, that's kind of the big takeaway. You're good with that? Sure. It's zero. Not necessarily. Here, the velocity is zero, and it stays. The speed is also zero, it stays zero. That's why. Look at this one. Here, you bring this one instant right there. You bring speed is zero. Yeah, but does it stay at zero? So here, the velocity is zero, but it's not the constant speed. Here, the velocity is zero and the acceleration is zero, so that's why this is constant speed. Crossing. One instant into there, so it's not constant. Right? A is not zero. You have an acceleration, not constant speed. Good. Let's take it. Right here. Take your cruise and do it. Okay, okay. Nice job. Nice job. Got it? Part A. Okay, what's the thing that I said to remember that it is? So this is what type of graph? How do you get acceleration? Derivative means you want every percent. What's the slope right now? Acceleration. Zero slope. Slope positive, negative, zero. Acceleration. Velocity. Oh. Velocity. Acceleration. Velocity is acceleration is. So that's what speed is. There's another way to think of it. Do you agree if you're sitting on this axis, shift velocity is zero? If you're going away from the axis, or VT plot, your speed is still coming. Here, your velocity is bigger and bigger, or it's negative.
Yeah, so like if for them I realized so we should just translate this area and say it's
Yeah.
equivalent to the other side.
From the horizontal. See, on the 18 plot. That's the only one where that works. So that's why I didn't mention it earlier.
Oh, yeah.
It's like a special case.
No, they're not the same.
18
Wait,
plot.
so,
Here,
oh yeah, so you would actually use this.
Here you're speaking to that.
This 24.
So this is the thing. So
I did
like if 4 meters to the left of the origin, it should position. That would show up.
The base.
So if you drew an XT plot, that would be. So you say 4 left. Yeah.
Oh,
So
wait.
in this case.
I thought just because the distance here is 28.
That
I'm
might
trying
be
to find
useful
the area.
here if you're trying to try plots. So if you try to make plots, you know
28 times.
that the issue position is taken.
Oh, yeah.
So that is only useful this last part if you're going to try to make the XT plot. I would tell you where you start.
16.
And all these areas will tell you how much
The other one is 1.2.
So go for it now.
Negative 20. Nice. Divide up by 2.
No, this is where it's initially located. If we figure out all these delta x's to add them all up, that would say -4 plus all of these tells you the final position.
Oh, I did the double negative.
Yeah. And so this is again one of those tricks. What's the difference
There
between
we
x,
go.
x initial, x final,
Ah,
delta
nice.
x?
No, that's correct. But
It's surprisingly tricky, right? Because you got so much along my brain.
Yeah.
I feel like
Add
you're
the negative.
so should I let you work it out?
Yeah.
So you were saying,
Nice. Nice. Out here, which thing? Which one? 27?
All right, thank you.
Anyways, what's up? That's awesome. Okay, well, I'll let you check, all right? Was there anything that like jumped out at you that was weird that you didn't get, or did you feel like you kind of understood most of the parts?
but I heard you not being confident.
But just kind of, basically, I get as close as I can, but still have at least 2 of them. Because you got grid lines up and down, you'll have grid lines on your test. So if you're looking for velocity at a certain point, or a slope, or if you're looking for a slope at a certain point, just make sure 2 points are close to it, but at least line up with 2 of the grid lines. Or version.
It looked very simple.
Exactly. So you gotta do it kind of close. So basically, when you get the slope, resist the urge to grab the easy ones. Now, exception, if everything's straight lines, this one you can grab it. Same slope, everything, right? But here, you gotta get one that's a curvy shape. You gotta grab slope. Okay? And here's another tip. If in doubt, show your work on to test it. Right? So if you show your work and you're wrong, I can at least look at it and tell that you did the right thing and try to get the question. Don't show your work. You just write down a number that's way off. You know what I'm saying?
Yeah.
So, yeah. All right. We did. You do it? Yeah. Okay. Right. Oh, it's just option. Do you have the, so you can do a couple of these. These are the so plots. So they're kind of good, especially if you're So that's a good way of looking at it. At least, like, if you get- you'll probably understand it easier. Definitely some kinematic. I don't want you to lose that. This one.
I got the F right.
What do you think, Owen? Doing all right? This is constant speed, 1-0. This is constant speed. Yes, 0, constant speed. This is aggressive. This is here, the edge is here.
So I don't know why it's. I don't know.
It's almost time to go. Just a heads up, just letting you know. I love these problems. If you look at the old test, I mean, the reason I spent all this time on it is because you know it's coming. And I love to put graphical questions on exams. So you want to be good at this stuff. All right. So that's cool. Somebody asked a question about the problems 2.29 and a fraction. If you see, there's like a whole bunch of those. Those are actually, I think, kind of, they're quicker in a way in that they're conceptual, right? But they're also, so you don't have to do tons of math on those. So that could be a different way to stretch your brain. Yeah, so, all right, I'm gonna let you guys, yeah, do whatever you gotta do. But if you're feeling uncomfortable with these, you've got to do a couple more. If you're starting to feel pretty good, at some point you'll be taking the practice test, and then you can verify you actually know what you're doing. If you don't, you can grab some more problems out of the recommended. Feel free to take off. If you have time, try to get the computers plugged in the right slot as best you can. All right. All right. I'll give you a couple more minutes to get out of here. I'm going to end the Zoom live stream because that was the most